Vibration visual inspection of piping guidance, ensuring safety and compliance through inspection methods. This topic refers to guidelines for the avoidance of vibration-induced fatigue failure in process pipework by Energy Institute. Purpose of vibration visual inspection of piping. Vibration visual inspection of piping systems is a critical preventive measure aimed at identifying potential vibration-induced fatigue issues before they escalate into failures. The primary objective is to detect as-built anomalies, operational conditions that may cause excessive vibration, and signs of wear or damage that compromise structural integrity. Unlike automated monitoring, visual inspection provides a direct, practical assessment of piping conditions under varying operational states. This approach is particularly important because vibration levels can fluctuate significantly depending on plant operations, such as changes in flow rates, valve positions, and equipment load. Inspectors should conduct surveys during different operating conditions to capture intermittent problems that might otherwise go unnoticed. The process involves observing physical movement, listening for abnormal noise, and feeling for vibration, all of which indicate potential mechanical stress. Furthermore, visual inspection complements other diagnostic methods by offering immediate insights into geometry, support adequacy, and maintenance practices. By systematically applying these observations, operators can prioritize corrective actions, reduce downtime, and enhance safety. Ultimately, the goal is to maintain piping reliability, prevent fatigue failures, and ensure compliance with industry standards for operational integrity. Indicators of high vibration and noise, fretting damage, and common locations. High vibration and noise are primary indicators of potential fatigue risk in piping systems. Inspectors should evaluate three distinct aspects: visible movement, tactile vibration, and audible noise. Visible movement often signals low-frequency vibration, while vibration felt by touch suggests low to medium frequencies. High-pitched noise typically corresponds to high-frequency vibration, which can be particularly damaging over time. When such conditions are observed, it is essential to document the operating parameters under which they occur, including pressures, temperatures, valve positions, compressor loads, and flow rates. These details help correlate vibration patterns with operational states, enabling targeted mitigation strategies. Ideally, vibration and noise levels should be quantified using specialized measurement tools, as outlined in related technical modules. However, even without instrumentation, careful observation and documentation during visual inspection provide valuable insights into system health. Persistent or intermittent vibration issues often point to underlying design flaws, inadequate support, or process-induced excitation, all of which require prompt corrective action to prevent fatigue-related failures. Fretting damage occurs when two surfaces in contact experience relative motion, even if minimal. This phenomenon leads to localized material loss and can significantly weaken piping components. Common locations prone to fretting include U-bolt clamps without resilient pads, resting supports lacking protective layers, deck penetrations where pipes vibrate against structural edges, and areas with loose insulation cladding. Additional risk points include partial clashes between adjacent pipes in contact with equipment such as cable trays or handrails. Temporary supports like scaffold poles or chains also contribute to fretting when left in place for extended periods. Inspectors should look for signs of wear, corrosion, or deformation at these contact points. When fretting is detected, immediate corrective measures involve separating the contacting surfaces and conducting detailed inspections to assess wall thickness loss. Preventive strategies include installing resilient pads, ensuring proper alignment, and eliminating unnecessary contact between pipes and structural elements. Addressing fretting early mitigates fatigue risks and prolongs the service life of piping systems. Pipe geometry and complexity, small bore connections or SBC geometry. Pipe geometry plays a significant role in determining susceptibility to vibration-induced fatigue. Complex configurations with numerous bends, valves, and fittings tend to generate higher levels of turbulent energy, which amplifies vibration. Thin-walled pipes are particularly vulnerable because they lack the structural rigidity to withstand cyclic stresses. Inspectors should pay close attention to areas near sources of turbulence, such as control valves or orifice plates, and verify that these sections have adequate support. Plant modifications, such as removing sections of piping, can create unsupported dead legs that further increase vibration risk. Evaluating geometry involves assessing alignment, spacing, and the presence of stress concentrators that could accelerate fatigue. By identifying these factors during visual inspection, operators can implement reinforcement measures, adjust support configurations, and reduce vibration exposure. Proper design and maintenance of pipe geometry are essential for ensuring long-term reliability and minimizing operational hazards. Small bore connections, SBCs, are highly susceptible to fatigue due to their geometry and loading conditions. The type of fitting significantly influences stress concentration at the connection point. Preferred designs include contoured bodies, welded tees, and fully back-welded fittings, while poor practices involve set-on or set-in configurations. Additional factors include the length of the connection, mass loading at the free end, and diameter reductions along its length. Longer connections with heavy valves or flanges create cantilevered masses that amplify vibration stresses. Thin parent pipe walls, often found in duplex alloys, further exacerbate fatigue vulnerability. The location of the SBC on the parent pipe also matters. Connections near anchor points are less prone to fatigue than those positioned midspan or adjacent to high-energy components. Inspectors should evaluate these parameters carefully and recommend bracing or redesign where necessary. Proper SBC geometry and support are critical for maintaining structural integrity and preventing premature failures. Pipe supports and their effectiveness, bracing of small bore connections. Effective pipe supports are essential for minimizing vibration and preventing fatigue damage. Visual inspection should identify missing or damaged supports, temporary fixes such as ropes or wooden blocks, and supports that lack sufficient stiffness. Common issues include goalpost structures without cross-bracing and pipe racks with poor lateral stability. Inspectors should also check whether supports function as intended. For example, thermal expansion may lift pipes off resting supports, creating air gaps that reduce restraint. Spring hangers must be correctly set to maintain proper load distribution. Fretting between pipes and supports is another concern, often resulting from inadequate padding or misalignment. Addressing these deficiencies involves restoring damaged supports, replacing temporary measures with permanent solutions, and reinforcing weak structures. Regular maintenance and inspection of supports ensure that piping systems remain stable under dynamic loads, reducing the risk of vibration-induced fatigue. Bracing small bore connections is a critical step in mitigating vibration risks, but improper bracing can introduce new problems. Common issues include using unsuitable materials such as ropes or cable ties, applying braces that lack stiffness, and failing to support free masses like valves. Braces that protect only the first weld or restrain the connection in a single plane provide inadequate support. Additionally, bracing to decks or adjacent structures instead of the parent pipe can lead to combined static and dynamic loading, increasing failure risk. Inspectors should verify that braces are correctly installed, bolts are tight, and gusset plates are reinforced to prevent punch-through on thin-walled pipes. Effective bracing involves securing the entire connection in multiple planes and anchoring it to the parent pipe for optimal stability. Regular checks and maintenance of bracing systems are essential to ensure long-term reliability and safety. Vibration control devices, other considerations, and environmental factors. Several devices can be employed to control vibration in piping systems, including gas-filled pulsation dampeners, viscous dampers, and hydraulic vibration snubbers. Inspectors should confirm that these devices are functioning correctly and have not deteriorated over time. For pulsation dampeners, verifying the correct pre-charge pressure is essential for maintaining effectiveness. Viscous dampers should be checked for lockup conditions and contamination due to damaged covers. Hydraulic snubbers must be inspected for signs of slackening or seizure, which compromise their ability to absorb dynamic loads. Additionally, vibration can transmit to adjacent pipework through shared supports or machinery skids, creating secondary fatigue risks. Identifying and addressing these transmission paths during visual inspection helps prevent cascading failures across interconnected systems. Beyond mechanical aspects, several additional factors influence vibration-induced fatigue resistance. Corrosion and erosion weaken pipe walls, reducing their ability to withstand cyclic stresses. Poor weld quality and mechanical damage introduce stress concentrators that accelerate fatigue. Environmental loading, such as wind, wave action, and seismic forces, can impose dynamic stresses on piping systems, particularly in offshore or exposed installations. Slugging in multiphase flow lines is another excitation mechanism that may not be apparent during routine operation but can cause severe vibration during transient conditions. Inspectors should remain vigilant for these factors and incorporate them into risk assessments. Proactive measures, including corrosion protection, weld quality assurance, and structural reinforcement, are vital for maintaining system integrity under diverse operating and environmental conditions. Summary and best practices. Visual inspection is a cornerstone of piping integrity management, offering a practical means to identify and mitigate vibration-induced fatigue risks. By systematically evaluating indicators such as vibration, noise, fretting damage, geometry, support adequacy, and bracing effectiveness, inspectors can detect vulnerabilities before they lead to failures. Incorporating checks for control devices, environmental factors, and maintenance quality further enhances reliability. Best practices include conducting inspections under varied operating conditions, documenting observations thoroughly, and implementing corrective actions promptly. Regular training for inspection personnel ensures consistency and accuracy in assessments. Ultimately, a proactive visual inspection program reduces downtime, prevents costly repairs, and safeguards personnel and assets, reinforcing its critical role in industrial safety and operational excellence.